First of all, thank you everybody for coming. This is my first year at REcon. They told me there'd be about 300 people here, which is okay on paper, but it's a little bit intimidating in person. But looking around, it looks like about 2/3 of you are hungover, so it's really only 100 people paying attention. I can manage that. What I want to talk to you about today is a relatively new concept that I call dynamic binary visualization. And this is a bold statement to make in front of a bunch of really talented reverse engineers, but I really view this as the future of reverse engineering, and I'll let you decide whether or not that's accurate at the end of the presentation. So let's go ahead and dive into some stuff. I've got to go through the background slides first. It's kind of boring, but my name is Domas. I'm an embedded systems engineer, part of the cyber innovation unit at a company called the Battelle Memorial Institute. Now, for whatever reason, a lot of people haven't heard of Battelle, but we are the world's largest nonprofit research and development institution, and we also manage a lot of the United States' leading national labs, so it's a pretty cool place to work. I don't want to be a shill for my company, but I do enjoy what I do, and hopefully you'll see a little bit of the kinds of things we do and be excited as well. So, believe it or not, what I want to talk to you about today is reverse engineering at a reverse engineering conference. But specifically, I want to talk to you about reverse engineering as a type of information analysis, and what I mean by that is we're given a giant binary blob, a huge chunk of information, and we need to decide what is this and what does it do? So when we look at RE through this lens, I think we always come across two ever-present issues, one of which is how do we conceptualize binary information? In other words, how do we make sense of what we're looking at? Obviously, our brains can't hold a gigabyte of ones and zeros, so how do we represent that information in our mind? And then how do we use our representation of that information to further our analysis and understand what's actually going on? So when we look at these two issues, I feel like there's two big problems that come up in the way that we do reverse engineering today. Yeah.
Something standard.
What's it look like now? Is that better? I think that's what it was. Good? All right. All right, something always goes wrong, but that's okay. Where was I? So when we look at reverse engineering from this perspective, I think there's two big issues that always come up. So with the first one, how we conceptualize information, I think brings up an issue that I sort of call the RE dichotomy. And what I mean by this is that we have two sort of polar opposite ways to conceptualize binary information. And it's sort of inevitable that we have to view information this way, but it's also sort of unfortunate. So in the first way, we have your traditional hexadecimal view, which I think is very flexible in that it doesn't tell us what this information actually represents. It's up to us to interpret the information, which means we're free to interpret it the way we want. So that flexibility is a big benefit of this view of information. It's also very exact, which is another big plus. There's no question that what I'm looking at here is exactly what the information is. The problem is it's also really, really complex to analyze information this way. So most of us tend towards the latter approach, which is something like a disassembly. This is a lot more rigid, unfortunately, in that there's not a lot of flexibility here. I can't really decide that this instruction here isn't a CLI instruction. It either is or it is not. And it's also governed by rules and grammars and other things that can fail us a lot, which are big problems, but it has a major benefit of being very succinct. It's really easy to look at information this way and understand exactly what's going on. So the problem I have with these isn't so much with either one. They both give us really good, really valuable information. The problem I have with these is that there's this huge chasm in between the two, and there's really nothing in there. We have no way to interpret information that's really somewhere between these two approaches. So that's the big problem I see with how we conceptualize binary information. The next issue I have is with really how we use that conceptualization. In other words, how do we answer what does this do or where's the vulnerability? How do we analyze that information? And I know a lot of guys who are really, really good at this part of RE. They can look at a layout of a function and tell you exactly what that function does without even looking at the instructions, just by the way the different nodes in the function are connected. Or I know other guys, I can hand them 100 pages of disassembly, and they can leaf through that in 5 minutes and point to the instruction that's vulnerable. The problem I have, although that's great talents to have, the problem I have with that is they often have a lot of trouble telling me exactly how they come to their conclusions. And I think the reason for that is that right now, reverse engineering is very much an art, which I think is sort of unfortunate because it's been around long enough. We should be able to make it into a science. So these are the two big things I want to address. I want to address this gap in our analysis methods, and I want to change RE from an art into a science. And these are pretty ambitious goals, but I think we can do this with the tools that we have available. And the two main things I want to use for this are a concept called visual reverse engineering, and this is going to address the way that we conceptualize binary information. And we can also use statistical exploration to address the other issue, the issue of how we use, or how we further our analysis with our conceptualization. Now, the statistical exploration side of things is kind of dry unless you're really, really into math. So I don't want to bog down in statistics and formulas. So I'm really not going to get into that side of things. I'll show you a little bit of what we can do with statistics, but if you really want to know the formula and the algorithms behind things, talk to me afterwards. What I really want to focus on is the part most people find more interesting, and the part that raises some eyebrows because it also causes a lot of skepticism. I want to address the issue of visual RE today to see how we can conceptualize binary information a better way. The fundamental idea we're going to address here, or we're going to approach here, is we can take a computationally difficult task, like conceptualizing 10 billion ones and zeros, and we can translate that into a problem our brains do better. So obviously our brains are not designed to handle binary information. What our brains are very good at is handling visual information. We've got incredibly powerful visual cortexes. So what we want to do is translate binary information into something we're really good at. In other words, we're going to find a way to traverse 100,000 pages of hexadecimal garbage in 20 seconds and understand exactly what is in that information as if we had just poured through it by hand. What we're really getting at is that if we can fundamentally change the way we process binary information, we can find entirely new and unexpected ways of making sense of it. So if you've never stared at a hex dump for 30 hours, you might be wondering, why bother? Well, there's a lot of reasons that I don't have time to enumerate, but the two biggest ones, I think, is that right now, all our RE tools seem to share a common flaw, and that's they are completely dependent on having a known structure. The issue with that is that information is evolving faster than our tools can keep up with. So every day there's a new file format, a new instruction set, something new that all our tools need to be able to adapt to just to keep up with the pace of things, and we really can't sustain that. The other big problem has to do with not the way information is evolving, but the way it's growing, and this is sort of colloquially called Gates's law. He summarizes that software is growing slower, or is getting slower more rapidly than hardware is becoming faster. It's sort of the counter to Moore's law. It says that basically if processor speed is doubling every 18 months, software is becoming that much slower. It's doubling in slowness every 18 months. And what that really means is if processors are executing more and more, or able to execute instructions faster, they're also executing larger quantities of instructions, which means we're processing more information than ever before. So information that we need to process and that we need to RE is growing exponentially. The ability of our tools to process that information and help us isn't growing at the same pace. So this is not a sustainable path that we are on. We really need to find a new way to analyze information. So I started looking at what was available out there, who had looked at this problem, and I was sort of shocked by the lack of research that had been done here. Really, I'd only found two guys who had addressed this in any sort of depth. One, his name is Greg Conti, and the other's name is Aldo Cortese. So I wanted to briefly look at some of the work they had done because both of these are really brilliant guys. So I wanted to start with Conti's work. He gave a presentation at Black Hat in 2010 that to date is the best Black Hat presentation I've ever seen. And it wasn't his style of presenting. It wasn't really anything that profound. It was just this really simple idea that had huge implications. So I want to look at Conti's work first. He had this idea, and he posited that even in unstructured data, there's some kind of structure. We just don't know what it is. And he suggested that barring any other information about what structures in data, we can assume that sequential bytes have some sort of implicit relationship. So Conti's dilemma was, how can we understand this implicit relationship if we have no idea what it is? He came up with a really simple, really profound solution. He said, we can take sequential bytes and treat those as XY coordinates. So we can take a string like REcon and just break that into byte pairs. So R in ASCII is hex 72, E is hex 65. That becomes 72, 65 as XY coordinates on our Cartesian plot. And as we begin to plot this information, we'll begin to see patterns. So when Conti looked at ASCII data, this is what he saw. So even though his algorithm had no concept of what sort of structure is involved in ASCII data, he was immediately able to pull out those relationships and visualize them. So what we're actually seeing here are all the structures that are implicit within ASCII information. So right here is an artifact caused by uppercase letters followed by uppercase letters. Here's an artifact caused by uppercase letters followed by lowercase. Here's lowercase, or here's lowercase followed by uppercase, uppercase followed by uppercase. These lines have to do with /r/n spaces. So without knowing any of that information, his very simple algorithm gave us a really neat representation of that data. And what he found is that no matter what type of information he looked at, he came up with unique visual patterns that let him understand what type of information was there. So images, audio, anything you looked at with his simple system had neat patterns associated with it. So that was Conti's basic idea. Next, I wanted to look at Cortese's work. And I had to crop most of Cortese's slides for the sake of brevity, but he had this neat idea that we could use a fractal called the Hilbert curve to present information in a more meaningful way. What he found is that when we map data to a Hilbert curve before presenting it to the user, we preserve more information. Most importantly, we preserve locality information, which lets us pull out small pieces of information that we wouldn't be able to otherwise see. So what I have here are two screenshots from Cortese's website, where on the left he's laid out data and shaded it in a very basic fashion, just left to right, top down, what he calls a zigzag pattern. So this is the most intuitive way to lay out data. The problem is it loses that locality information. So by going through the Hilbert transform first, that's what he's showing on the right, the same data set through a Hilbert transform, you're all of a sudden able to see structure that you wouldn't be able to see with a traditional view. So things like this tiny little square here has to do with a discrete structure within this data set that you can't even identify with a more traditional approach. So Cortese's interesting idea was to put data through these transformations before visualizing them in order to get more information out of them. So both of these guys had really cool ideas, but I looked at their work. They had a few snippets of software available, but I tried to use it for actual RE, and it just fell short. It wasn't interactive enough. It didn't give you the control that you needed for serious in-depth RE. So I really wanted to build on their ideas and take them to entirely new levels to find a way to understand information independent of formats. So that's the key here that's supposed to set all of this apart from everything else that's out there, is we're going to find a way to look at data without knowing what's there. So that gives us tremendous advantages when we're dealing with some sort of unknown code or when we're dealing with format deviations. So everybody knows malware likes to adjust the format of things to throw off your analysis, or proprietary structures when you're pulling off a piece of a firmware from some embedded system, something you've never seen before, something for which specs aren't available. All of those things can be done a lot more easily if we have tools that are well suited to dealing with data independent of its format. Really what we want is a way to explore that format a priori. So I developed some software that I call Cantor Dust, that's named after a serious badass, my second favorite mathematician, Georg Cantor. And really what this does is just illustrate some concepts. I'll use this software today to highlight some things, but it's really the ideas that I'm trying to get at. So it doesn't need to be the software. I encourage people to explore these ideas on their own because I think there's a lot of really neat opportunity here. So all this really began with a very embarrassing mistake that I sort of have to divulge here. I spent 30 or 40 hours looking at a hex dump, thinking that, well, I'd already reverse engineered this unique compression algorithm, and I thought this was going to be a piece of compressed data that was going to lead to some malware. So I spent a long time looking at this, and at the end I figured out this turned out to be a picture of a kitten. It was not at all what I was looking for. It wasn't the elite malware I thought it was. So how could I make a mistake so profound when I consider myself to be a decent reverse engineer, well, it's really easy to get bogged down in information when you're trying to look at it at this level. So at that point, I sort of had this epiphany that I think Conti had years before me, in that I was looking at hex values, but I couldn't care less about the actual hexadecimal numbers in front of me. Like here, what does D8 mean? I have no idea, and I don't care what D8 means. It means nothing apart from the bytes around it. So it's never the hex values I'm interested in. It's the relationships between them that I'm interested in. So I sort of started questioning, why am I using tools to look at these hex values when all I really care about is their relationships? Why don't I have tools available to look at the relationships between binary information chunks? So I started developing this Cantor Dust project in my spare time, and it actually sort of morphed into a pretty neat, I think powerful RE tool that I want to present to you today. So let's actually dive into this application. So I always want to give this as a hands-on demo. I could have recorded this beforehand and then just talked to it, but I think that takes away from some of it. Unfortunately, if it's hands-on, that means I sort of have to focus on my keyboard, which means you're welcome to just stare at the top of my head for the next 40 minutes, but I think you'll get a lot more by looking at the screens. So what I did is I fired up Cantor Dust. I want to look a little bit at the interface we have here first. It automatically loads notepad.exe for us to analyze in some more depth. So what we have here is on the left some navigation panes that lets us select a small window, or any window, within our data set. Now here's the data just laid out in the most intuitive fashion possible. So the window on the left lets us select a coarse window. The window on the right lets us select a fine grain window inside of that. Over here is our main visualization, where we're going to use these visual translation mechanisms to understand what kind of data is inside of our window. And on the far right here, we have the different plugins that we've developed to translate this information in different ways. So let's go ahead and actually start looking at some information. I'm going to drop in a sample of x86 code here. And we're going to look at this in Conti's two-tuple system, or rather, Conti called these digraphs. I call them two tuples because I've extended these to more dimensions. But essentially, this is what you find when you look at x86 code. And one of the defining features here are these horizontal and vertical lines. So let's look at x64 as well. What you'll see is a similar pattern of horizontal and vertical lines, but they're in different locations and they have different intensities. So one of the neatest things about Conti's approach is that similar classes of information have similar patterns associated with them, but they're always going to have a special unique pattern that lets you immediately identify them. So the key here is that I can actually tell you that this is x64 code from looking at the hex dump, but that's only because I've done this for 3 years. It takes a long time to learn to analyze information at this level. It takes all of 3 minutes to learn to recognize x86 or x64 or anything at this visual representation. So I can drop in something that I'm completely unfamiliar with, like PowerPC. I've never read an instruction of PowerPC in my life, but I can instantly tell that I'm looking at machine code here because I see the same patterns that I've seen before with these horizontal and vertical lines. They're in places I'm not familiar with, so I know it's an architecture I haven't seen, but I do know exactly what type of data I'm looking at. So I think that's a pretty powerful ability. Now, what we found is that Conti's original idea was pretty neat with this two-tuple system, but you can get a lot more information out of things if you extend it to more dimensions. So what we did is we took that into 3 dimensions to come up with a 3-tuple system. So what I did is I dropped in notepad.exe right here. And what we're seeing are the visual representations inside of Notepad and the window I've selected. So we can actually scrub through this window and essentially watch how the patterns change in order to understand the different types of information inside of notepad.exe. And again, the idea being that I can instantly recognize these visual patterns, whereas trying to analyze things at a hexadecimal level takes years and years. So let's see, there's also, I guess what we also found is there's no reason to limit your analysis to an individual translation mechanism. You can actually tweak a translation mechanism for the data that you're trying to extract. So for example here, what I'm doing right now is translating data to 3 dimensions. I can actually translate it to 2 dimensions and then layer those on top of each other. And sometimes this can give me more information or sometimes less information than the other translation mechanism. So by selecting the correct parameters for a certain translation mechanism, I can really narrow in on the type of data that I'm trying to analyze. So Going further, we can actually, right now we're translating to a Cartesian coordinate system. We can translate that instead to a cylindrical coordinate system, or well, that was spherical. This is cylindrical coordinate system. The point being, we choose the translation parameters that are best for the type of data we're trying to do. So at this point in development, I got a little carried away with having fun. So I had some fun with these particle effects, because I'd never used particle effects before. So I just littered my poor code with Easter eggs that really have no purpose. But you know, at 3 in the morning, when you've been looking at hex all night, it can be fun to have a break. So anyways, when that's done, you can go back to actually being productive. I don't know. I always felt like if everything you develop has a point, you sort of failed as a software engineer. So it's fun to just have fun sometimes. So those were sort of the extensions of Conti's ideas we've looked at. Let's look at Cortese's ideas as well. So Cortese had this idea of the Hilbert transformation, and what we're looking at specifically here is a visualization of a metric, of an entropy metric translated through the Hilbert curve. So what can entropy tell us? If you're not familiar with entropy, it's essentially a measure of randomness. And there's a lot of really important things that randomness can tell us about a file. So things like encryption keys, packed data, code obfuscation are going to have unusually high entropy. And a lot of times we're not just interested in high versus low entropy, we're interested in different entropies. So for example, in x86 or any language, if you try to obfuscate your code by adding in all sorts of jumps and weird code constructs that you wouldn't normally see, you're implicitly changing the entropy of your code. So right away, by trying to obfuscate things, you're calling attention to yourself. And we can view that through entropy. So a couple examples. Malware, of course, loves to pack itself, so we can toss some malware into our application and visualize its entropy. So pink here is high entropy, blue's low entropy. So obviously the bulk of this malware is going to be packed, but by trying to find the low entropy sections, we can immediately find the entry points to this malware. So nothing too profound here, but just one of many ways in which entropy and other metrics can be very useful for us. I also mentioned different entropy, so I'm going to drop in my favorite hex editor here, and I won't name it because I don't want them coming after me, but you might recognize it. What I did is just drop that in, and we're visualizing the entropy inside of this executable. So obviously there's a big region here of very high entropy. So I was curious as to what that was. We can use our little windows to zoom in on that a little bit more. And sometimes I can get it, but if we pull up the hex editor here, and try to look at where this high entropy begins. You'll see right here is PNG. This is the beginning of a PNG header. So PNG is just a compressed image format. If you're just a reverse engineer, that's really not something I'm too interested in. I don't know if you're a forensic analyst, images might be very interesting to you. But for me, I wanted to move on and find something else. So I also noticed this little region down here of unusually high entropy. So if we try to zoom into that, and I pulled it up in the hex editor, it wasn't really anything I recognized, but if you dive into that a little bit more in IDA, you'll see this is actually the key checker algorithm for this particular application. And essentially they compressed it, trying to obfuscate it, trying to hide it from you, but in doing so, called undue attention to it. So just an example of how entropy can give us some valuable information for our analysis. So let's actually put all this to work and go back to notepad.exe and actually dissect the file. So of course we could drop notepad into IDA, and IDA would break down notepad for us and show us what each individual region was. But IDA can only do that because it knows exactly how a PE executable is laid out. It has a well-defined structure that IDA is relying on. As soon as you deviate from that structure, tools that rely on that sort of information are going to be useless. So we want to figure out all the same information without ever relying on that kind of structure. So what I'm going to do is switch to our 3-tuple visualization and scrub through this and discuss a little bit about what we're seeing as we go through this. So right away, this is the visual pattern I associate with x64 code, and I can recognize it because of the exact placement of these horizontal and vertical lines. I've seen it a couple of times in here, and you quickly learn to pick up on these visual patterns. And as we begin to scrub through, what you'll see emerging are some smaller cubes inside of our large outer cubes. So there's a cube here, cube here, cube here. What that tends to be is the visual representation of ASCII text. And if you look closely, you'll actually see that these cubes are projected onto the face of the outer cube. So there's a projection here, a projection here, and projection over here as well. And what that actually tells us is that these are null terminated strings inside of this file. So as a reverse engineer, that means absolutely nothing, but it's just an example of how you can get unexpectedly detailed information from this abstract visual representation without ever having to look at things at a close-up binary level. So if we continue scrubbing through this, what you'll see come up are artifacts associated with a bitmap image. You'll see a streak going through the middle of the cube here. Does this all show up okay? Yeah. You'll see a streak going through the middle of the cube, and then that streak's also projected onto 3 faces of the cube. This tells me that there's an unused alpha channel inside of this image. Again, not too useful as from a reverse engineering perspective, but just an example of how you can get really detailed information from these visual representations. As we continue scrubbing through, you're going to see the image eventually overcome with static, which tells me that I'm entering a compressed region inside of notepad.exe. And as we approach the ending, we're going to see a different representation of bitmap information. And this time it happens to be the icons within the file, which you can almost see appearing over on this side over here. But we can dig down a little bit more depth. So one of the things I wanted to look at was this region here, which we decided was some sort of bitmap image. So you can actually use your feedback from one visual representation to assist in your analysis with another. So we can pull up our metric map here and adjust some of the parameters for how this is laid out in order to pull out the image inside of that region that we're looking at. So if we do that, we can see that, let's see. We can see that it's actually the genuine Windows logo sitting inside of notepad.exe, which doesn't even appear in the application, but in typical Microsoft fashion, that bloats 10% of their software. So the neat thing here is our application has no idea how to render a bitmap image. It doesn't know what a bitmap image is because it has no concept of format. But by changing the way we translate that information into images, we can pull out some of these details. So that's sort of a basic use case of how we can use these types of things to pull out the information that we're interested in. So those are sort of the ideas that other people came up with and that we've extended on. But we've also added a lot of our own ideas. And one of the biggest, I think, is we saw earlier how we could use these different visual representations to understand what type of data we're looking at. But I wanted to automate that task. I figured if a person can look at these images and decide what they are, a computer should be able to do the same thing. So what we came up with is what's called basically a naive Bayesian classification, which is a basic statistical algorithm. And we form these n-gram models, which are chunks of n bytes. And we throw all this stuff into a model, do this Bayesian classification algorithm on it to classify all the data within the information that I've given the application. What we can do at that point is take any other piece of information and ask our application what looks like this. So for example, I can toss in notepad.exe. Not knowing where the x86 is, I can find x86 from some other file and say, what looks like x86 inside of notepad.exe? And it will highlight the regions that look like x86 based on this Bayesian classification algorithm. So for x86, that's not too useful, but for some other things, that becomes really important and a really valuable technique. So for example, with customer proprietary formats, something you're not familiar with, something your current tools can't process, as long as you can find one sample of that to give the application, it can pull out that information for you. Or unique instruction sets. Malware loves to invent its own instruction sets. Well, if you've never sat in IDA for hours and hours just trying to differentiate between code and data, you might not really appreciate how difficult that can be without a definition for the instruction set. But with this type of algorithm, all we need to do is find some instructions that we know of, and even without defining how those instructions are generated, we can give that to our application. It will find statistically what else looks like these instructions. And we're not quite to the last part yet of identifying code and data features, but that's where we're headed with this. So for example, I have a giant block of x86, and I want to know where are the encryption algorithms in here. Well, encryption is going to have a certain statistical signature. It's going to have a higher density of some instructions than others, and we can automatically identify those changes inside of our model in order to pull out that type of information from the code I give it. So I can find one encryption algorithm and say what else looks like encryption algorithms in here, pull that information out. So this is a really neat tool that we'll see in action in a little bit. I also came up with this idea that I call probabilistic parsing. So the issue here is that parsing gives you valuable information about a file, but it relies on knowledge of an instruction format, and I didn't want my software to know anything about any specific format. I didn't want it to be dependent on that sort of thing. So I wanted to find a new way to parse information. So in conventional parsing, there's two main approaches. There's recursive descent parsing, which is what IDA uses. You give it a starting point. It sort of follows the path of execution. If there's a call made, it follows that call. If there's a jump, it follows that jump, and it parses in that fashion. Then there's linear sweep parsing, which is something more like objdump, which basically starts at the beginning, and it just goes through in a linear fashion. It doesn't care where execution branches to. It just moves to the next linear instruction. So both of these methods have their pros and cons, but both of them have one serious con, and that's that they rely on a complete definition of that instructions grammar. So we came up with a way through statistics to identify some of the same basic features. So what you're looking at here in this screen is essentially a call graph from an application that I gave our software, and our software is able to pull out key features like commonly called functions and function linking to trace function connectivity without ever relying on a knowledge of the instruction set being looked at. So we'll look at this too coming up because I want to look at an actual case study, because people are always skeptical of binary visualization and whether or not visualization can actually be useful in this type of thing. So I want to look at an actual use case of how we can use our software to do something pretty neat. So what I want to look at is attacking Intel BIOS. So there's a group called the Invisible Things Labs. If you're not familiar with them, it's just a small group of researchers. I think it's 3 guys and a girl. But they have just come up with some of the most incredible exploits I've ever seen. And they gave a presentation at Black Hat in 2009 called Attacking Intel BIOS. Essentially what they showed is how they could bypass EFI signing protection. So just a little bit of background if you're not familiar. EFI is basically the BIOS replacement. And EFI is supposed to have a lot of benefits, one of which is being a lot more structured, one of which is being a lot more secure. One of the ways they're more secure is they allow images to be signed and checked before they get flashed. That way you don't end up with unsigned code inside of your firmware. So just a little bit of background here on what Invisible Things discovered. They discovered that the actual image that gets flashed isn't signed. It's only an envelope that's checksummed. Inside that image, though, are individual modules. Each of those modules are signed. So when they started looking through these modules, they found signed module, signed module, signed module, unsigned module. So the obvious question is, why would you have an unsigned module if you're going for security? Well, it goes back to how BIOSes are developed. So Invisible Thing looked at this unsigned module as a potential attack vector. And the way BIOSes work is, and EFI for that matter works, is you have a couple key developers who develop the bulk of the code, and then they sell their code to OEMs, the people who actually sell you your laptop. So the BIOS developers wanted the OEMs to be able to add their own splash screen to the code without the BIOS developer having to be the one to sign that. So they let the splash screen be unsigned so that the OEM could add their own. So it's an obvious attack vector, and Invisible Things found a fairly conventional exploit by looking at this. So even though they can't update the code, they found that they could update the splash screen. So all they had to do is look in some of the public EFI code that's developed by Intel. This public EFI code gets distributed to IBVs, which is independent BIOS vendors. So if you can find an exploit in Intel's code, it's going to be applicable to almost any BIOS or EFI system out there. So they found a very typical buffer overflow involving the bitmap width and height in this file. So they could get an overflow and they could get execution. Unfortunately, Invisible Things left out a lot of the details of their exploit, for better or worse. And one of the things they left out is that no one is really EFI right now. BIOS vendors have a lot of legacy code that they're not willing to give up. So they gradually adapt that code to more and more fit in with the EFI structure. But what that means from our perspective, for somebody trying to actually implement this exploit, is we're not dealing with well-structured EFI like we'd like to be. We're dealing with very, very unstructured BIOS, It means there's a lot more headache, but it also means there's a unique opportunity to use our tool here because our tool is perfectly suited for unstructured data. So invisible things covered the actual exploit. I don't care about that part anymore. I want to figure out everything else and show you how we can actually figure out how to implement this exploit using binary visualization. So step one is choosing a victim laptop. BIOS is not something you can just toss into an emulator very well. It's not something you can virtualize very well. You really need a physical piece of hardware. So I found this thing sitting in my closet, held together by duct tape and thumbtacks. I really don't care if I brick this thing. So first step is going to be choose that and grab a BIOS update from the vendor's website. So once you download the BIOS update, it's just an exe. So quick RE, you can extract the firmware image. What you see when you open up this exe, it's a bunch of strange little strings here. They're basically their attempt at obfuscation to hide the command line arguments for this. So specifically, you come across a string, and when you subtract 1 from each of these characters, you end up with write ROM file. So you just run this executable with the write ROM file flag, and all of a sudden it dumps out a binary image, which is actually what will get physically flashed onto your system's firmware. So some quick image RE. I'm going to pull this up in IDA so that we can actually do this interactively. So to be able to analyze images like this, you need to know a little bit about x86 architecture and specifically where the processor starts up when it first resets. But if you do know that information, you can pretty quickly find this guy right here, which does some basic cache initialization and then falls into this function loop down here that has no return. So all this function loop really does is execute this list of functions here. Most of these aren't too interesting. They're just hardware initialization things, but I was particularly interested in the very last function here because since this loop doesn't return, this last function must hand off functionality to something. So if we look in here in a little bit more depth, what you'll find is custom decompression routines. So this little algorithm they have here is not like anything else that exists anywhere else. So it's not something you can just throw your conventional tools at. What that means specifically for us is they're giving this decompression algorithm a certain module located at this location in memory. And again, the problem here is this is an entirely custom module. It has no standard headers. It has no standard format. It has nothing that your common tools are going to be able to analyze. So again, that's sort of where all your normal tools fall apart, but where Cantor Dust comes into play. So when I looked through the entire binary, I didn't see anything that looked even remotely like a splash screen, even looking at it in Cantor Dust using those types of things. So so what I decided is that the splash screen must be embedded in one of these compressed modules. So I guess step one was try to find who else calls these decompression routines. We found one place already, but to find the other modules, we need to find who else calls this. So unfortunately, only one other guy calls this, and nobody else calls him. Which means that the only other places that are doing any module decompression are inside the module that we already found. So you could spend a lot of time running down this rabbit hole where one module decompresses another, decompresses another, decompresses another, and you could waste a tremendous amount of time doing that, just trying to find the one compressed module that you're interested in. But this is the perfect opportunity to use some of the algorithms we talked about earlier, where what I'm going to do is pull our IDA database into our application here. And we're going to use the Bayesian classification algorithm I talked about. So what I did is I took the one module we already found, cropped that out, and fed that as a template into our software. And what I'm going to say is find other stuff that matches the patterns that we're seeing there. And it's going to essentially try to analyze this entire file here and pull out the other modules for us. So it just finished its analysis. It found a lot of interesting things. It found some x86 over here, some x86 here. I think somewhere here is going to be the x86 we were already looking at. It found some unknown compressed item here, some ASCII here. Most importantly, here's the module that we gave it, and it says, well, here's something that looks like that module. Here's something that looks like that module. And here's something that looks like that module. So obviously, here's a giant chunk that look like that. It's either one giant module or it's an entire set of modules. So that's what I wanted to focus on now that our statistics was able to find that for us. So I wanted to figure out where this thing began. So we can zoom in on this in a little bit more depth. Basically trying to figure out where these modules begin in memory. So it turns out they're right on this border here at FFE1, blah, blah, blah. So what I did, assuming that these are the other modules, is I found the starting and endpoints using this application, and I cropped them all out. So what I did then is we can essentially, we want to decompress those modules at this point. So if you're familiar with IDA, you really ought to know about a IDA plugin called x86mu by a guy named Chris Eagle, a really smart guy, knows a lot about IDA. So with his plugin, you don't even need to understand this decompression algorithm. You can just run it through x86mu, point the right registers to the beginning of our modules, and it'll decompress everything for us. So at that point, we end up with a bunch of extracted modules. So the obvious thing to do when you've got a bunch of files and you don't know what they are is run file on them. Unfortunately, every one of these modules is, again, a custom thing. It has custom headers that we don't understand and that our tools don't understand. So file basically tells us everything's data except for these two false positives, which are common false positives in files. So again, we're sort of at a dead end with conventional tools because of the custom data types that we're seeing. So again, what I did is I catted all the files together so that I could easily dump them into our application. So what we're going to use is, going back to Conti's two-tuple system, I'm going to try to figure out exactly what information is in these files. Specifically, I'm looking for the splash screen. So I'm going to look for a visual signature that I've seen before, something I associate with images. So as we scrub through this, and hopefully I'll be able to catch it because it does go fairly fast. We're basically going to see a visual representation of all the different data types that are within this set of files. And right there is actually what we're looking for. So it's a little bit hard to catch this the first time if you haven't seen this pattern before. But this is a pattern I've seen several times that happens to be associated with 4 bits per pixel bitmap images. And once we know that, we can actually use our other systems to pull out that information, just like we did with Notepad. So right there we can see the Dell splash screen. So in a matter of almost no time at all, we found the splash screen that could have been incredibly difficult to find with conventional reverse engineering methods. So at this point, it's fairly easy to repackage that module with our own screen. But before we do that, to look at going back to the original exploit idea, this turned out to be mod E. So if we drop mod E into a conventional hex editor and sort of look through this, what you'll fairly quickly find is that this actually follows the bitmap file format. So why didn't our conventional tools tell us that this was a bitmap? Well, it turns out that they stripped the bitmap header, the bitmap signature. The bitmap signature is just the characters BM at the beginning of a file. So if we just take our same file and add those exact characters back in, all of a sudden all of our conventional tools start working again. So O10 can instantly break this file apart because it understands the format of a bitmap file. And in particular, it can give us the width and height that we were particularly interested in for this particular exploit. So by modifying these values is how we'll get the code execution we were looking for. I didn't really care about that part so much. I just wanted to repackage this thing with my own splash screen. So we can repackage this and try to reflash it, but something comes up. It doesn't work. And we already discussed that the modules are signed, the bitmap's not signed, so it shouldn't be a signing issue. What it goes back to is that envelope issue. All the modules, all the signed and unsigned modules exist in a checksummed envelope. We need to fix the checksum if we've changed one of these modules. So Next task is going to be find the checksum routines within this image, which is, again, not too easy, but what I decided is I didn't see any checksum routines in the initial firmware image that we dumped out. It was all hardware initialization stuff. All it did was call a bunch of hardware initialization routines, decompress this module, and then jump to that module. So I got to assume that the checksum check is going to occur fairly early on. So I really started my analysis with that first extract module, which is this ROM3B here. So let's pull that guy up in IDA. So once again, we load this into IDA, and IDA can't tell us the first thing about this file because IDA has never seen anything like this before. So again, our best tools are fairly useless in this situation. So what I want to do is pull this into CantorDust again and see what we can find. Here's where I'm going to rely on the statistical parsing method that we discussed earlier. What this is going to let us do is essentially visualize function calls within this file without ever having to parse the thing. So I can change my window to any location and see what the function calls within that location look like. Now, unfortunately, when I'm starting out, I really have no idea where anything is or where what I'm looking for exists. So I need to select the entire thing from my window. And I'm actually going to crank up the number of nodes here so that I can get more information inside of my function graph. And what this is essentially now a 3D representation of all the function calls made within this module. What I'm looking for are the functions, well, if I had nowhere else to begin, I'm looking for what gets called the most, which is what it's shading for me right now. So what our software determined is that statistically speaking, there's almost certainly a function right here that's called more than any other function. So if we go back to that location in IDA, just as statistics told us without knowing anything about x86, there is in fact a function here. And I'm not going to walk through the reverse engineering of that function. It turned out to be nothing too interesting, just another function dispatch thing where it would just call another function for you. So the second most called function was this guy right here. So I wanted to look at that in a little bit more depth. And again, if we go there in IDA and create a function there, just as statistics thought, there is a function here. And if we dive into this guy, you'll see it accessing a series of characters. Here's space, percent, plus, minus, 0, 9, HCSXD. You might recognize these as placeholder tokens for a printf function. So D is decimal, X is hex, S is string, C is char. So this is essentially a printf function here, although if you look at it in a little bit more depth, it's not going out to your screen. It's actually going out to a port on your computer. So this isn't a printf that the user would ever see. It's a printf a developer would see, which tells me that this is actually a debug printf. So that is definitely something I was extremely interested in, and I wanted to investigate more. So if we do that, we can, here's the debug printf that we already identified. What I want to do now is, since there's so much garbage here, we want to crop this out, and I'm going to change this to a two-dimensional system now that we have isolated what we're interested in. So at this point, it's telling me the function called the most is, again, this printf. So I'm not so much interested in what's called the most. I'm interested in what's calling printf the most. So I'm going to change the way that I actually render these to shade it by who's calling printf the most. So what it shows here is that this function, again, statistically speaking, without knowing about x86, is almost certainly the function calling printf more than any other. So if we go there, just as expected, it is calling printf an awful lot, but it turns out this is really nothing interesting. So where to go next? Because all these other nodes are about the same size. So I didn't really have a good idea of where to progress, except that two sets of these stand out more than the others. Mostly this guy and this guy and this guy and this guy. These stand out more because these nodes are connected, which tells me not only does this node call printf, but one of its children calls printf as well. So because of that increase in complexity, that seemed like a logical place to begin further analysis. So if we pick one of these and go to that location in IDA, toss this guy up, this is boot B is going to be boot block flash recovery. Now, flash recovery algorithms are pretty neat things, but not really what I'm interested in right now. So I wanted to go to this other set of information here. If we go over here, I had already found this now that we've given it some starting points. This calls debug printf with validate RBU, that's remote BIOS update, CRC. So that's what we're looking for, which we found almost immediately. And if you don't know anything about CRC algorithms, there's a lot of different types, which is why we really needed to find this rather than just update our module with some known CRC. We needed to figure out what CRC they were using. So this tells us right here, this is the offset within the binary image at which to place our CRC. Here we'll find CRC has some different magic numbers to start with. Here we find their magic number for their CRC that we're going to need to use to repackage our file. And here's their actual CRC algorithm. So at this point, we have everything we need to know to repackage this and adjust their flash screen and fully implement Invisible Things exploit. Again, I didn't care about their exploit. I just cared about getting to that splash screen. But just to sort of reiterate what we've done, we used, I'm about to die here. That's what happens when you're in a hurry. You don't plug things in. All right, that's embarrassing. We used probabilistic parsing to find a couple of the key functions. Namely, we found a debug printf, which we could use to find the CRC checksum routines. Once we identify those, it's really easy to repackage our image and get our custom flash screen onto this thing. Unfortunately, I bricked this about 4 hours later on a different attack, so he's in the garbage pile now. But if you go to our website at some time soon, I'll post a video of a similar attack on a similar system. So with CantorDust, this took me about 9 hours, most of which was spent in reverse engineering their custom compression routine. I told you you could use x86mu to decompress modules, but at some point you need to recompress them, which means you need to understand their exact algorithm. Without CantorDust, it took me 37 hours. So I actually went back to this, did these same routines without having our software available, even knowing exactly what I was looking for, even knowing I wanted to find that debug printf, even knowing I had to find this CRC routine, even knowing how the modules were packed. It still took me 37 hours to find everything using conventional approaches. So what I really hope I've shown is that these visualization techniques aren't just Hollywood make-believe anymore. We can actually get useful information out of these that can be a really powerful tool for reverse engineering. So that's sort of where we stand right now with the software. I wanted to briefly touch on where we're headed. So goal number one is to improve the user interface. I really designed this software for myself, so it makes sense to me how it works, and to me it's plainly obvious. Control-Shift-Alt-F-Q2 is exactly what you do to rotate an image. Unfortunately, I give the software to other people, and they don't understand. So we really need to improve the user interface to make this a usable tool for the common person. Incidentally, my favorite editor is VI, and I think a lot of that has sort of trickled down into the software, for better or worse. So we want to get this in the hands of people, but not until it's usable. The next major thing we're trying to accomplish is integration into all of our current tools. So I think CantorDust is really powerful by itself, but it becomes exponentially more powerful when you integrate it into the tools you're already using. So the tools we're already using sort of suffer in that they depend on knowledge about structure. So if we can use our current software to feed them knowledge when that knowledge is absent, things become really powerful. So we saw a little bit of how this integrates with IDA already. And IDA does a really good job when it already knows what it's looking at. But as we saw already, when IDA doesn't know what it's looking at, it does a pretty lousy job. So what we want to do is completely integrate this into IDA. We want to replace IDA's navigation bar with useful information about the statistics we've gathered. We want to automatically integrate these function graphs that we can generate from statistics, integrate our other visualization methods to really allow you to interactively explore data within a framework you're already familiar with. So that's sort of the useful stuff we're looking at. But one of the things I really like about reverse engineering is when you're on a path you're not happy with, when you're not getting the results you want, or when you just want to do something different, it's really easy to explore some other path. So once in a while, I need to do that kind of thing. So I've also started looking at some pointless things, and I thought one of the neat things to do with the software would be to make it completely hands-free. So I got this little device called Elite Motion from a guy at work. This is going to be on the market pretty soon, I think. Essentially, it's like a tiny Kinect, except it focuses on hand motions and finger motions. And it lets you have really fine-grained control over your system. So I started coding for this thing, and it turns out to be incredibly easy to use and really easy to add code for. So it took all of a day to start integrating this thing into the CantorDust framework. And I actually have the plugins available now to rotate your images with your hands. Unfortunately, that's all you can do right now. So it would have made a really lousy presentation if I was rotating stuff and then jump back to my computer to use the mouse to do anything meaningful. So I didn't really want to demo that today, but it's potentially coming in the future. So I don't know, is this useless? Maybe, but 2 years ago, I would have said the whole concept of binary visualization is useless. And I've sort of done a 180 since then. So if I was so wrong about that, maybe I'm wrong about this too. Although there are ulterior motives, because I don't know, once in a while, a girl will ask what I do. And I get to say, I'm a cybersecurity researcher at the Patel Memorial Institute. I do work for the Department of Defense. And they get really excited. That sounds awesome. Well, what do you actually do all day? Well, I really sit in a dark basement for 14 hours a day looking at hexadecimal. And you can't say hexadecimal to an English major, so you have to say looking at ones and zeros, which sounds even worse. So their eyes go dead, like you had just said, I flip burgers for a living. So I wanted to make reverse engineering as cool to other people as it is to me. So what I really want to get to is being able to say, you know that movie Minority Report with Tom Cruise? That was based off of my life. I go into work, I put on my RE gloves, I dive through 3D information, I find the exploit, and I hack all the things. So I think this is closer than it might appear to be, because we're really getting there with this software. So bottom line conclusions, we need better ways to understand and analyze information because our current tools just can't keep up. RE is going to stagnate if we stick with what we've been doing. So my point isn't use the software I demonstrated. I think the software I demonstrated is neat. That's because I wrote it. My point is really explore these ideas, start thinking differently, because we can do things better than we're doing them right now. So if you're interested in getting a copy of this, I do have a website that I haven't updated for about 1.5 years, so you can try the website. It's probably not going to give you anything because I don't have a copy of it on there. You can try to email me at thedeltaaxiom@gmail.com. I'm notoriously bad at replying to emails, so if you've tried to contact me before there, you probably didn't get a response. I apologize for that. That's probably not the way to go either. So instead, I'm going to put up an email from a coworker. He doesn't know I'm putting his email up here, so he's not going to be too happy when this goes online. But you can bombard him with emails all you want, and he's a pretty responsible guy, so he should get back to you about getting a copy. We'd like to have a closed beta in the upcoming future to really get this in the hands of real reverse engineers to see how they can use it and what they want to get out of it. But really, we've just gotten started. I'm hoping the awesome host of this conference will have us back next year and we'll have even better stuff to show you. So that's all I got. Thank you, everybody, for being here. I don't know, did I go over on time? I went a little over on time, so maybe I can answer 1 or 2 quick questions, and afterwards you can just track me down if you want to know anything. And again, it's this third one that you want to bother, not the one above it. Yeah.
So your Android models, are you training them with headers, with files with headers, or what's the decision recall?
So the question was about Ngram models and how we train them. So it's a good question, one with sort of an ambiguous answer. We can train them with the headers attached. The headers tend to throw off your results. You want a pure sample of what you're giving it. The catch is that the whole point of the Ngram model is that you don't need to understand the data exactly. So I might not know where a header begins and ends. So as long as I can give it a sample of information where 95% is the type of information I'm after and there's only 5% junk, it does a pretty good job. We're still actively working on that portion of it, and there's a lot of room for improvement.
Okay, have you thought about switching it out with like an SVM and other classification algorithms, or are you like don't know? Is there a reason you chose naive Bayes?
The reason I chose naive Bayes is because it's easy.
Yeah.
So we have thought about other things. We haven't had time to research it in depth, but yeah, we'll be looking into that. It's a good question. Yeah, I developed this on my own time. The catch is I work for Patel, which is a great place, but they own it. It doesn't matter how I developed it, which means they're responsible for how it gets released and what we do with it in the end. which in some ways might be bad. It means it's probably not going to be open source, but in other ways it can be really good, because I think with the company's support, we can take this a lot further than I would have been able to take it by myself. Yep. Yeah.
How does the probabilistic parsing work? Is there one of those black boxes? Oh, we can parse
It's right.
Okay,
It's
that's great. You've given raw bytes, if you have the hexadecimal, that's all you know. And so how are you constructing this graph?
So the question is, how does the probabilistic parsing work? And it's sort of a black box in the presentation, and the reason for that is it's complicated. The general approach is we're sort of trying to exploit commonalities found in how almost every language makes function calls and jumps. And one of the approximations we can make is take any substring of bits from your data set and treat that as some kind of offset to some other location in the file. And just generate every possible offset you can, and then run it through some filters to pick out what probably is and probably isn't. And it's an approximation. And as you saw in the demo, it's an approximation that works pretty well most of the time. But there are false positives. But in any disassembler, even a grammar dictated disassembly, there's going to be false positives. So.
Slide a window that you choose, and then you look at how much that window is occurring, and then you draw the edge. I'm just confused what the nodes are and what the edges are.
So you come up with a. So the question is, what are the nodes and the edges in this probabilistic parsing? You come up with a set of edges based on these the binary strings that you're looking at, that you're interpreting as offsets. So you end up with this incredibly massive set of possible edges. You filter out based on frequency, which ones occur the most often, which nodes are going to be pointed to the most often. Then you do have to take it through one more step where you refactor these edges into an actual graph, which I could spend another 3 days on. So, yep. I did, which afterwards, when I presented this to my coworkers, they said, this stuff already exists, and I thought, oh, I wasted a lot of time. But it's sort of fun to do things yourself, and it's fun to explore that yourself. So yeah, all the graphics, everything else, I used XNA as my graphics framework, but the particle effects, the physics are all homegrown kind of things that are sort of specially adapted for this tool. All right, this will be the last one, and then anybody else can talk to me afterwards. So the question is, have I tried it on data that's not byte aligned? I have not. So we have my group at Patel is divided into sort of software guys and hardware guys. It's mostly the software guys who have been looking at this. And for us, we mostly deal with byte aligned data. Now the hardware guys who are pulling, pulling firmware off of ROMs, looking at raw bits of things, they're a lot more interested in the other side of things. I haven't had time to look at it, and I don't think they've had the interest. So the answer is no. All right, thanks everyone for coming. You can talk to me.